over at the other side. LT2. Alright, so tonight I'll start off with tutorial 1. It's pretty straightforward. Most of the questions relate to fading. Alright, and then after the tutorial, we have a short break. And after that, we will move on to the next topic, which is on medium access control. Okay? Alright. I hope you had a chance to try out some of this. So it's not intended as homework that you have to hand up, but at least you have to try it, okay? Right. And then after every tutorial that I've gone through, I will upload the answers. Okay. Right. I'm not sure if I've got all the things that I wanted for this module up yet. Let me just check. Okay. So right now I've not uploaded the past year papers and quizzes, so I will upload that later so that you can try it. Okay. Right. So let's see what we have here. So question 1, we have a mobile user travels at 80 kilometers per hour. So transmit at a carrier frequency of 850 megahertz. Experiences really fading with a signal to fade margin of a squared over 2 sigma squared of 0.01, and assume that C is 10 to the 8 meters per second. So determine the average rate at which the signal envelope falls below the fade margin. So that's the first one. Average fade duration, average interfade duration. So those are pretty straightforward. All the formulas we went through already last week. Alright? So these are the things that are given. We are given that it travels at 80. We are given that the frequency, carrier frequency is 850 megahertz. And a squared over 2 sigma squared is 0.01, and C is 3 times 10 to the 8. Those are things given. Alright? So in part A, we are supposed to find this guy. Right? Average rate at which the signal envelope falls below the fade margin. In part B, we are supposed to find P, average fading rate. And in part C, we are supposed to find the average interfade duration. As I said, the formulas are all there. We already covered that last week. You just plug in the formulas and you get that. So that's pretty straightforward. Part D, determine the received carrier frequency if the mobile is moving directly towards the transmitter. So if the mobile is coming to the transmitter, you have this Doppler effect. Okay, so whatever is the carrier frequency, it will be increased by the Doppler effect. So for part D, it will be Fc plus Fd, maximum Doppler frequency, which you can determine. Okay, and for part E, for a digital transmission system using quadrature phase shift keying, operating at 200 kilobits per second, is the really fading slow or fast? Okay, so to find out whether it's slow or fast, right, you have a data rate of 200 kilobits per second, right? And it's quadrature phase. That means that is the same as, that means 2 bits make one symbol. 2 bits make one symbol. So that would be 100k symbols per second. Alright? So the symbol duration will be 1 over 100 times 10 to the 3. That's the symbol duration. So the question is, do you have many fades over this period? Or the fade occurs over many symbols? If you have many fades within one symbol, that's fast fading. If the fade occurs over multiple symbols, that is slow fading. Got it? So you got to compare this value with the value of this guy, 1 over NA. Because 1 over NA tells you how frequently the symbols are occurring. So if NA is 10 fades per second, that means the fade will occur over what? A long period, right? Okay, 1 over 10. Okay, or you can also compare against this. This is the duration of the fade. So there are multiple ways you can compare. If either 1 over NA or PF is much smaller than this value, then it's fast fading. Because many of them are occurring within one symbol. Got it? Huh? Okay? However, if these two values, one or this, either one is fine, is much bigger than this value, then it's slow fading. Okay? Right? So I've told you all the steps that you need to do. The equations are all inside your notes. Right? I won't go through every line and rewrite it, but show you just the steps. Okay? So if we do that, also because LTs are not particularly good for working out things on a smaller classroom on a whiteboard. So can you all see at the back what I've written? Cannot see, too small. This is what the problem is, too big an LT. Alright, so I would suggest next time you come closer to me, be a little bit more cozy. Okay? Right. So I'll try to write larger. But the screen is okay, you can see. Okay? So as I said, the first one is NA. That's the formula over there. Alright? The formula is here. Okay? The formula is here. Alright? So the first thing you have to do is to find maximum Doppler frequency, which is V over lambda. Lambda is FC over C. So plug it in, you will find that FD is 62.96. Then you plug it inside here. You're already given this guy. Okay? Alright? Which is here, 0.01. So square root of that will be the first one. Square root of that will give you this. This value is 0.01, so this is 0.1. Again, substitute inside, you will get 15.63 fades per second. Alright? Similarly, for the average fade duration, which is B, again the formula is there. You have already found FD to be 62.96, which is over here. Okay, 62.96. So again, you plug it inside the formula. All the values are already known. Plug it in, you get this guy, and then work it out to have this value. Okay, so this has an average fade duration of 0.637 milliseconds. 0.63 milliseconds. 0.0000637 is 0.637 milliseconds. Okay? Alright? Similarly, for the interfade duration, which is part C, you do the same thing. You got all your values already, plug it inside here. You calculate, it's 0.06 3 milliseconds. So the duration between them get is 63.3 milliseconds. 63.3 milliseconds between plates. The fade is 0.6 milliseconds. Okay? So this is about 0.01 milliseconds, right? 1 over 100. Right? 1 millisecond. Okay? Then part D is FC plus FD over here. FC is known, 850 megahertz. FD you calculated out, 62.96. So you add those two together. So that's the frequency that the signal is arriving at the receiver when the other guy is walking towards the receiver. Okay. And finally, to compare those two, as I mentioned, that's your symbol rate, 100 kilosymbols per second, because it is QPSK modulation. All right, so the symbol duration is 10 to the minus 5, as you can see here. All right, NA is 15.3, so you get the time between fades is 0.64. So the symbol is much shorter than the fade. So that means the fade has to occur over multiple symbols, and this is slow fading. Questions? No question. All right, not we go to number 2. Okay, most of the questions are very similar. Okay, question 2. A mobile transmitter travels at a constant speed of V meters per second. It experiences Rayleigh multipath fading. The received single envelope undergoes 100 fades per second. So now, what is this? This is N, right? NA, right? So we know NA now. Okay? That's okay. And the normalized fade margin is 0.01. Is it big enough now? Okay. How fast is the vehicle traveling if the carrier frequency is 1 gigahertz? So, okay, these are all the data that is given. So we want to find V. Again, you go back to the formulas. V is related to which one? You want to find V, the vehicle speed. V is related to FD. Remember? Right? It's related to FD. Okay, so if you can find FD, you can find V. Because this guy here will give you lambda. Okay? Okay, so from here, you know FC, you know C. 3 times 10 to the 8. So you can find lambda. Alright? FD is related to V and lambda. So you can find FD. Okay? After you find FD, you can find V. Okay? Use the formula for this. From this formula, you can find FD. Right? If you recall previous answer. Here. This fade margin are already given to you. This is 0.01, so this is 0.1. This is given to you, this is 100, therefore you can find FD. Alright, FD is V over lambda. So if you know FD and you know lambda, you can find V. Got it? that's part A. Part B, how fast would the vehicle travel if the average duration of that the envelope falls below the fit margin is 10 milliseconds? So in other words, he's saying now, if TF is 10 milliseconds, find V. Okay? So again, you have the formula for TF. Alright, given that formula, you can find FD. Having found FD, you can find V. Got it? Huh? So that means using the formula, from there you can find FD, from there you can find V. Okay, those are the 3 steps. Alright? So if we do that, this is what we have over here. Right? So that is the data that you are given. NA is 100. The normalized fate margin is 0.01. Speed of propagation is 3 times 10 to the 8 meters per second, and FC is 1 gigahertz. So using this formula, NA is 100. This guy is 0.1. This guy here, A squared over 2 sigma squared, is 0.01. Substitute inside, you can get FE to be 402.95. Then you know that FB is related to V and lambda by this guy. And lambda is C over FC, which is this guy. Again, plug all those numbers inside, and you get the speed of 120.84 meters per second. Okay. Very fast. Okay. Any question? Then the second part, you are given TF, 10 milliseconds. Again, the same thing, the formula is there. Then you find FD. FD found already, you find the speed. In this case, all right, you can see that. Plug everything inside, you can find FD, which is 4. Then from there, you plug it inside here, you know C, you know SC. Plug it inside here, you get 1.2. So that's the speed. All right. Questions? All right. Okay, the next one is a little bit more interesting. Okay, we have a mobile. Most of this came from past year question, by the way. So you know what's the standard now. Okay. Okay, mobile terminal, MTA, as you can see there, my little MTB over there. Okay. Traverses a path as shown in figure Q3. Alright, so that is the blue arrow here. It traverses this path, it's moving along here. The arc represents the cell boundary within which the mobile terminal will be serviced by base station BSB. Okay, so that's the base. So that is the limit of the cell, if you like. Okay, the radio coverage cell. So the radio channel operates at a carrier frequency of 2 gigahertz. So you know FC now. The speed of radio propagation is 3 times 10 to the 8 meters per second. So you know C. And the normalized fate margin, which is A squared over 2 sigma squared, is 0.01. Okay. When do you encounter the maximum fate level crossing rate? That means when do you get the maximum NA? Okay. So if you look at the speed of the vehicle and the direction of the vehicle is not going directly to the antenna or going directly away from it. It's going at an angle, right? To the antenna. Okay? So we need to determine under what circumstances do we have maximum motion? between the vehicle and the base station? Under what circumstances? Maximum relative motion. Can you guess? Will it be here? No, right? It's going to be here, right? Maximum relative motion towards the base station. Similarly, at this point, it is the minimum relative motion because it's going away. Okay? Alright? So, we need to find what is the maximum relative motion in this direction. So, if this is 60 degrees, this is 30 degrees, right? So, it must be V cos 30. That is the relative motion between the transmitter and the receiver. Okay, now once we figure that out, everything else is the same as before. Because now we know the relative motion already, which is V cos 30. Okay, the rest is the same. Okay, so once you found that, of course you can find maximum fade level crossing with this maximum NA. Okay, you can also find, yeah, I think that's the only part of the question. Okay, so that's what we do. Okay, so we have B, which is 15 meters per second. We have the carrier frequency, which is 2 gigahertz. We have the propagation speed, which is 3 times 10 to the 8 meters per second. And the normalized phase margin of A squared over 2 sigma squared, which is 0.01. So as I mentioned, the maximum relative speed will be at V cos 30, V cosine 30 degrees. Okay? So you know V, you know cosine 30, of course you can find the relative. So that will be 12.99 meters per second. Okay, so now you know that. Again, you can find the maximum Doppler frequency FD, which is given by this formula. Put in all those values, you'll find that the maximum Doppler frequency is 86.8 Hertz. Then substitute that into the equation for NA. So this is 86.8. You know this is 0.1, this is 0.01. Plug it in, work it out, and you have 121 fades per second. Okay. Question. Okay, this is about delay spread. The mean delay spread in a particular environment is 1.5 microseconds. What is the maximum symbol rate before inter-symbol interference renders communication impossible? So, we're given delay spread. Mean delay spread, let me call it tau bar, is 1.5 times 10 to the minus 6. Okay? So the maximum rate that you can go is that. That's it. That's the maximum rate. Okay, the reciprocal of the delay spread. That's question 4. Alright? And the answer is pretty straightforward. 66.67 kilosymbols per second. Before ISI, inter-symbol interference, prevents you from decoding the information. Okay? That's question 4. And finally, one more. That's it. Okay, a mobile radio user travels at 20 meters per second and communicates at a carrier frequency of 2 gigahertz. So you know V, you know FC. The speed of light is 3 times 10 to the 8 meters per second, and the normalized phase margin again is 0.01. Okay? Determine the probability that the received signal is in a phase. Okay? So let's think about this. If you look at a signal envelope, it's going like that, right? Sometimes it's high, sometimes it's low, right? Okay? And if you have a straight fade margin, whenever we hit a fade here, we know there will be a lot of errors. Correct? Because that is the minimum level of signal quality that you need to be able to communicate effectively. Okay, so the question is asking you, what is the probability that the signal is in a fade? Okay, so we know that the time between fades is 1 over NA, right? Because NA is the number of fades per second. Yeah. And the time that is in a fade on the average, correct? So what's the probability of fade? This divided by this, right? Example. If the time between fades is 10 seconds, and the time in the fade is 1 second, what's the probability of fade? 1 over 10, right? And there's something. Okay? 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 So of course you can put in all the numbers later, huh? Right? Because you have all the formulas. Okay? And then you can get your answer. I'm just giving you the steps. Okay, the second part. If the user moves at a slower speed, so now you change the speed, will the probability of being in a fade increase or decrease? Okay? Now to know that, of course you have to plug in the formulas. Where does V appear? FD, right? FD is V over lambda. So if this formula still has a FD inside, then that depends on speed. But if this formula doesn't have an FD, that means it doesn't depend on speed. Agree? Huh? Okay? Yeah. Because if you notice on the formula depends on FD and A squared over 2 sigma squared, which is the normalized fade margin. Okay? Right. So you got a general idea. Right. So the first part, we calculate FD, plug it in, okay? D is 20, FC is 2 gigahertz, C is 3 times 10 to the 8 meters per second, and normalized fade margin is 0.01. Alright, you calculate FD, and it turns out to be 400 over 3. Then you can calculate NA, it turns out to be 33.089. Then you calculate TF bar, and it turns out to be 0.03. Okay? So the probability, as we saw here, is this times this. You multiply the two of them together, it is 0.0995. 0.0995. Alright? That is in the fade. Now, if I take the formula for NA and TF, if I plug it inside here, so that is my TF, this is my NA. Clean it up, this is the result. If you look at the result, is FD there? No FD, right? So that means whether you move faster or slower, the probability of fading is the same. Because there's no FD. Okay? Alright? There's no FD. It only depends on the normalized fade margin. Interesting, eh? The probability of you being a fade is only dependent on the normalized fade margin, not the speed. Okay? independent of the speed. All right? Any question? Okay, no question. So if no question, before we break, I show you a little demo. By the way, you guys are. I hope you can. Usually Murphy tells me when I want to do something, it will not do. Okay, let me give you a background to this. In this campus, it's a pretty big campus. We have pervasive Wi-Fi access across the entire campus. Okay, there are more than 200 buildings in this campus. All right, and as a result of that, we have close to something like 5,000 wireless access points across the campus. Over about 5,000. Okay. So, about 2 years ago, we did a project that not only did we want to provide wireless access to the internet, but we also want to do Wi-Fi device location, Wi-Fi device detection, to detect where are all the devices. All right, and after we've detected all the devices, then we can use this information for a variety of purposes. Okay, one is you can use it for research. Okay, so what sort of research can you do? Well, you can learn about how crowds gather in different places of the campus. You can learn about how crowds move about in different parts of the campus. If you are into smart buildings, research smart buildings, one of the things you need to know, are there people in the building or not, right? Okay, if there's no people in the building, you can turn off the lights, you can turn down the air conditioning, save energy. If somebody is coming in, you turn it up again, right? Okay? If your ability to detect whether people are in the building is very accurate, if, there's a big if, and if you have certain rooms or offices that have, say, labs that has hazardous material, radioactive material, chemical hazards, biological hazards. Suppose a disaster happened. If you know whether the room is occupied or not, your emergency response will be different, right? If a fire happens, if you know nobody's in the room, you can apply a much more aggressive fire mitigation. If you know there's somebody in the room and the fire is happening, what's your first thing? Is it to put out the fire? No, it's to rescue the people, right? So these are the things would be useful potentially if you can detect where crowds are. That was the intention. Okay, that was the intention. So we did all these things, all right? Unfortunately, the accuracy is not very good. Okay, we bought an extra software from Cisco, and you know Cisco is one of the most expensive. Right? Each software for each AP is about $100. So 5,000 APs is $5 million. 500,000, not 5 million. Come on, guys, wake up. Anyway, it's expensive, huh? But it's not just the software. You have to put in the back end to receive all this data. Okay, and then we archive all that. So what I'm going to do now is to give you some idea what is happening. Okay, let me pick some location. Somehow the one in this room I wasn't able to pick it up. I'm going to go to the architecture and engineering zone, and I will go to a room which probably I hope you all will recognize. E306. That's where all the seminar rooms are, right? You know E306, right? Next to the dairy. Okay. The blue dots are the APs. The red dots are all the Wi-Fi devices that are detected. All right, and this is live. Live. Okay. Now you see dots hanging in the air. Remember, this is the 6th floor. 6th floor. All these dots over here are not supposed to be there because it's on the 6th floor outside. Unless you can float like Peter Pan. Or one of the superheroes. Okay? So unfortunately, the accuracy of this localization software from Cisco is in the range of having an error of 2 to 10 meters. Alright, and that's why you get those dots outside the building. Okay, 2 to 10 meters. Okay, but nevertheless, if you consider the dots to be part of that floor, it's pretty safe. Part of that floor. When is it not safe? When you're near the window. Because when you're near the window, you get the leakage of radio signals from APs that are one floor above you, as well as APs from one floor below you. So when that happens, when you get those extra signals coming in, they mess up your localization. Okay? Alright? Which is why there have been startups in Singapore who have been trying to provide localization service, say, in shopping malls. Okay? And the problem with shopping malls is that in many malls, the central area is an open multi-level open area. Many malls. Okay? So when that happens, it's very hard to determine whether you are on floor level 2, level 3, or level 4, because the signals are all over the place. Alright, so that's one of the disadvantages of Wi-Fi based localization. Okay, I can show you another one. Let's see. Did we have LT2? LT2 was it? LT4, I just checked already, cannot be. Alright, the other one is, library is pretty good. Library is pretty good because they upgraded the Wi-Fi access points there. So level 4 is where you have the main entrance of Central Library. I don't know. Have most of you visited Central Library? Yeah? Yes? You know where Central Library? Just behind here, right? Oh, this is computer center, not Central Library. C4. So you see less red dots outside. But there are not too many people inside there. Not too many. The situation is very different during reading week. There will be many red dots there. So in fact, library is keen for someone to help them develop an app to tell them where are the seating areas. So if you have an app that does that, you don't have to look for seating areas. You see, those places that have less red dots, you go to those places. You know what I mean? Okay? Right? So this is an example of a Wi-Fi communication network being enhanced to be also a Wi-Fi sensor network. This is an example. Okay?
So,
yeah?
This doesn't mean that the people inside have to connect to the Wi-Fi.
No. It's detect the device.
Detect the
device. Yeah. Alright, detecting the device.
The device means the phone.
Because all of you, I'm sure you set up your smartphone and your laptop such that once you turn it on, or once you come on campus, it automatically connects to the NUS Wi-Fi system, right?
If I turn on the Wi-Fi.
If you turn on Wi-Fi. Who has not turned on the Wi-Fi here? Let me ask you. You have not. You're a rare one. You're an outlier. True. Honestly, who has not turned on? I know of one now. Who else have not turned on? 2. Any more? 3. Be brave? Come on. I tell you, it will be less than 5%. It will be less. Why? Because our natural behavior is that we want to get free Wi-Fi access to the internet. Unless you want to pay $100 data plan. Then you have unlimited volume, right? But how many of us go for that kind of subscription plan? No, most of us don't. We want the cheapest plan, not the most expensive plan. Right? That's why we turn our Wi-Fi on. Right? Okay? So the problem is that, yes, we turn it on, but then again, when we are stationary, there is a high likelihood that both your smartphone and your laptop is on. So there is a certain amount of over counting. Right? Over counting. When you are stationary now. So this system detects Wi-Fi devices that are what we call associated, that means you log in already, as well as when you are in a probing mode. So for example, you get out of this room, there may be some access points under the above the ceiling here, you cannot see it. If you get out of this room, the wireless link that you have with a particular access point will get weaker and weaker, right? At some point, it's so weak it will break, right? So once it breaks, you are probing, find where's the next access point to log on to. That's called the probing mode now. So this system can detect both probing devices as well as associated devices. Okay, all right? So I thought I'd just give you an example. All right? I wish I had more examples to give you. We had another system which was also very good, but I think right now it is sort of semi-decommissioned. Yeah.
How did it achieve the localization? Do they use like 3 points or?
I don't know. It's proprietary. It's whatever Cisco use. Okay. All right. And it's pretty lousy. Okay. To be honest, it's not only Cisco's fault. Because when Computer Center, or now we call it NUS IT, okay, when they install the Wi-Fi access points, especially the older ones, the Wi-Fi access points were not properly georeferenced. That's the name for it. Georeference means that I know exactly in what position, what XY coordinate it is on this floor. It was not exact. The user acceptance test did not include that. So what the vendor did was that after they installed it, said, oh, this Wi-Fi access point is near this room door. They have things like that. So why is that important? It is important because the Wi-Fi access points are the reference points to do your localization. So if your reference points are not accurate, how can your localization be accurate? If you say something is near this door, near this door can mean anywhere from 2 to 5 meters away, you know? Right? As long as you say, oh yeah, okay, near this door. See, from here to here is 7 meters. Which door? Okay, so the APs themselves were not properly georeferenced, and as a result, the localization is also not very accurate. All right, okay, yeah. Okay, one more comment, and then you can take a break. So recently, we actually had another project which is partially decommissioned. Most of you doing the master's course, is this your second semester on campus? Second, right? Were you here in the previous academic year? No, not yet, right? So we had a system that was running until the last semester, until the previous academic year. If you go into our NUS shuttle bus, you notice a blue banner that says you've got Wi-Fi, right? That doesn't work anymore, right? It doesn't work anymore. So that was a project that we did where we hotspotted all the shuttle bus. So that when you walk into the shuttle bus, it automatically connects to the NUS network. Alright? But when you connect to the NUS network, doesn't mean that you are connected to the internet. Because the hotspot has to be connected in some way to the internet. Okay? So to do that, we implemented a heterogeneous network with StarHub and a vendor. Okay? A heterogeneous network is a network that uses multiple technologies. Okay? So there were basically three technologies that was used. The hotspot, of course, is Wi-Fi, 802.11. We all know that. inside the bus. To allow the communication between the bus and the internet, we use a communication technology called dedicated short range communication, DSRC. Okay? DSRC is a technology that was intended for vehicle to vehicle and vehicle to infrastructure communication. Alright? Okay? It was intended to be a communication platform that would provide the communication fabric for things like autonomous vehicles and so on. So for autonomous vehicles in the future to work, the vehicles have to talk to each other, you know. Alright, you cannot be blind. If you're blind, then you cannot see each other and you cannot do things like what we call vehicle platooning. The vehicle platooning means that you have a lead vehicle, the rest all follow this lead vehicle. That's platooning. Okay? So, we set up a number of base stations, about a dozen of them, which is not enough to cover the whole campus. But if you get close enough, you will use the base station based on DSRC. But if you're far, then it will backhaul to 4G LTE. Okay, so if you're playing a YouTube video, the switch over is very fast, so you don't even realize it. Okay, it's quite seamless. Okay, so we put that system in at the same, so that there's an onboard unit. We've got an OBU. Put an onboard unit inside, which has the wireless router to provide a hotspot, which has the DSRC RF inside. You have the 4G LTE RF inside. You have the controller so that you can do all the switching. Okay, right? On top of that, we also have the GPS, so you can track the motion of the bus. Okay, and we track it every second. The bus. So we collect all this data. All right, and I said because it's decommissioned, I cannot show it to you now. But when we were operating, we have a dashboard, very nice dashboard. Okay, you see the map, then you see where are all the base stations, then you see all the buses moving, in live, moving, and then you see how many buses are at that moment using DSRC, how many are using 4G LTE, what's the volume of data using DSRC, volume of data using 4G LTE, and so on. All right, so we can do all this. Okay, so unfortunately that is gone now. Associated with that project was to put in the fibers to all the bus stops so that we can put a Wi-Fi access point. Okay, so that is now under renovation right now because the vendor has pulled out. So NUS IT is going to replace the previous equipment with Cisco boxes or other boxes so that you can have Wi-Fi at the bus stops. Okay, so that means from the building to the bus stop, you are covered completely until you leave the campus. Okay, all right. So again, when we were doing this, we could collect all the data. So if you're doing studies on crowd dynamics, for example, you have all the data. So some of my old students, I tell them, you know where you are? You know how to find out? Because all this data is publicly available. Unfortunately, the archive site is down. We're having some problem with the servers. But once it's up, I can tell you where it is, and you want to look at the data, you're welcome to look at the data. Okay? Of course, there's a problem, privacy, Okay, because when we gather all this data, we know who's the user, we know your MAC addresses, blah, blah, blah. But we don't look at your data, because it's all in the headers. Okay? So we have to encrypt all this. Okay? Encrypt all this. So I think to students, find out where you are. We tell you what is the encryption algorithm. Take a MAC address, go on the online site, find the encrypted address. Find this address inside the database. You're there. Okay? It's quite fun, like, you're doing things like that. Okay? So I thought I'd just show you this. And during the course of the module, occasionally I will show you little demos here and there. So to instill some inquisitive nature within you. Alright, we do most of the work, we do a lot of work on localization in the lab. Okay? KE here is really. Alright, but she's going to move on to privacy prevention. Okay. We actually have a test bed. Again, that site is down. If it's not down, I can show you the test bed. Isang is also inside that lab, so you know what I'm talking about. Alright, we have an IoT test bed in the lab. So Prof. Tam and myself, we are using that data. Alright, the test bed is one wing of the IQ building on level 2. So we have about 23 nodes. Huh? Is it 23? Sensor nodes, 23, right? Something like that, yeah. 23 sensor nodes. So we created our own Wi-Fi sensing access point using Raspberry Pi 3. Okay, so it can sense all the Wi-Fi devices. Plus, it also can sense environmental conditions like temperature, humidity, light level, audio level, and something like about a dozen different chemicals: carbon monoxide, nitrogen oxide, hydrogen sulfide, whatever. There are all these chemical sensors. Okay, so we have all that data. All right. When that part is up, I will show it to you. Okay. I must save all the stories for these 6 weeks. I cannot tell you everything. I have other stories to tell you, but hang on. Okay, let's take a break. All right. I don't think I can finish media access control tonight. All right. I will only be able to finish maybe 2/3 of it, because the media access control will also cover standards like Bluetooth, Zigbee, Sigfox, and LoRa. Now, some of you may have heard of this. Definitely you've heard of Bluetooth, huh? But the other 3 you may or may not have heard of. Okay? Those are standards that are coming in which are supposed to be relevant to Internet of Things, IoT. That's why I want to cover it. Okay? This module is not intended to be a super academic module. Alright? Super academic is a lot of math. It's intended to give you some exposure to the wireless network and sensor network technology. Okay, that is the intention. And that's why I give you examples. That is not all theory here. Okay? Right. Okay, let's take a break. And then we will continue in about 7:15 or thereabouts.